Hello, welcome to the video. Today's video is going to be about why legacy systems never die. And quick disclaimer, I am synthesizing work across economics, social technical systems, and reliability engineering here. I won't cite every paper on the screen, but I'll mention the key ideas and names so you can look them up if you want. So to begin, thinking about legacy systems, they persist not because engineers are irrational or resistant to change, but because they are embedded in social technical systems with high switching costs, accumulated trust, and institutional coupling. Once software becomes infrastructure, replacing it stops being a technical problem and becomes a systems problem. That's the intuition in one sentence. And if you want the reasoning behind it, here are the core ideas. The first one would be switching cost and path dependence. In economics, there is a well-established idea called path dependence. Early choices shape what becomes feasible later on. One of the classic discussions comes from economist Paul David, who used the QWERTY keyboard to show how adoption patterns, training, and coordination can matter as much as raw technical merit. The important point here is often missed, which is path dependence doesn't mean early choices were bad. It means that once a system becomes widely embedded, switching costs start to dominate. And those costs aren't mostly about code. They show up in retraining people, renegotiating contracts, rectifying regulators, and updating downstream systems that quietly assume existing behavior. And W.B. or W. Bryan, author, later formalized this with the idea of increasing returns, meaning the more a system is adapted, the more valuable it becomes to keep using, even when alternatives exist. It might be better. And it may be technically superior across many dimensions. So over time, replacement stops being a question of technical superiority and becomes a question of coordination, risk, and institutional cost. You can see the same kind of path dependence even in a lot of physical infrastructure, like the US residential grid standardized early on around roughly 110 to 120 volts, while much of Europe and Asia, maybe except Japan and maybe a few other countries, standardized around 220, 240 volts. Once that choice was made, everything downstream adapted to it, like wiring standards, outlets, appliances, safety codes, building practices, and training. Today, switching would mean not just changing voltage, but retrofitting hundreds of millions of homes, replacing appliances, updating codes, and coordinating across utilities, manufacturers, and regulators. So when you think the efficiency gains are real, but their coordination costs dominate. Another one would be social technical systems and institutional memory. Meaning one of the reasons why legacy systems are difficult to replace is that they're not just technical artifacts. Over time, they become part of a broader social technical system, meaning a system where software, people, procedures, and incentives co-evolve. In practice, this means mature systems observe workflows, informal practices, and coordination mechanisms that are only partially captured in documentation. A lot of what keeps organizations function is tacit, meaning learned through use, not written down. And research in social technical systems, our organizational routines consistently shows that technologies tend to succeed when they align with existing institutional practices. not simply when they are technically better or superior. This helps with helps with the explanation why large-scale system replacements often struggle because the software changes, but the surrounding organization oftentimes doesn't. And this mismatch creates new new failure modes that weren't visible during the design. So when a legacy system appears fragile or opaque, it's often because it's doing coordination work that no single component was ever explicitly designed to handle. And the subsection of this is really about law and regulation and institutional lock-in, because there's also legal dimensions to this that reinforces the same pattern. So in-law systems aren't just judged in isolation, they're judged against risk, reliability, and institutional expectations. For example, cases like the T.J. Hooper show that courts don't always accept industry custom as sufficient. That really creates incentives to stick with systems that are already understood, certified, and defensible in hindsight. So in a similar fashion, the Hand formula in negligence law explicitly balances burden, probability, and loss. When the downside risk is catastrophic, the burden of change can outweigh efficiency gains. Even though it might be no-brainer, there's still the burden. So once the system is embedded in regulation, audits, and reliability frameworks, replacing it isn't just a engineering decision, it becomes a legal and institutional one. This becomes very complicated as it is a system in itself with many parts that require coordination, and I think a lot of people have that intuition already. For engineers, though, this means replacement decisions are often constrained less by what's possible and more by what's defensible. And another reasons why legacy system last is really about reliability, risk asymmetry, and known failure modes. So another reason I would say legacy systems persist has less to do with performance and more to do with risk. In safety critical and mission critical domains, risk is asymmetric. Failures are rare, but when that happens, the consequences are often severe. In those environments, systems are often valued not because they're elegant, but because their failure modes are known and bounded and have been stress tested under real operating conditions. So this idea really shows up clearly in research on high reliability organizations, places like aviation, nuclear power, or industrial automation. They often use triple redundancies and so forth, where the primary goal isn't necessarily optimization first, but avoiding catastrophic failure. So from that perspective, replacing a functional system introduces uncertainty, and uncertainty itself becomes a form of risk. So stability can domain improvement, even when better decisions or better designs, I should say, exist on paper. So I will say this doesn't mean older systems are inherently safer. It means unknown failure modes can outweigh marginal gains. And I will say this is huge, going into risk a little more, but this would be a separate section about the legacy system. I will say why large-scale rewrites are risky. This also helps explain why large-scale system rewrites are very difficult. Rewrites tend to have high variance outcomes. Some succeed, many struggle, and downside risk is often disproportionate to expected gains. The issue is rarely the new technology itself. It's that the rewrite assumes the surrounding organization can change as cleanly as the code base. So in practice, though, workflow incentives and informal coordination often remain the same, which creates a mismatch between how a new system is designed and how work actually happens. So that mismatch produces new failure modes, meaning it's not because the new system is worse, but because it's operating in an environment it wasn't designed for. So I would say this isn't an argument against modernization and automation. It's an argument that replacement risk is often underestimated, often or sometimes very severely. And why should I care about this? Well, how is it related to engineering, AI, ML? I will say if you work in AI or ML and feel like good models don't translate into real change, this is probably usually why. About the large scale rewrites are risky. And this could be controversial, but I will say why the legacy system and about all these previous sections, why ML systems becomes legacy quickly is related to these. What's interesting is that even modern machine learning systems can become legacy surprisingly fast. Empirical work across multiple domains shows that deployed models tend to degrade over time. Data distribution shifts, human behavior adapts to predictions, and feedback loops change the environment and model operates in. So in machine learning, this is studied under concepts like dataset shift, concept drift, and performance predictions, meaning the idea that predictions don't just describe the world, they help shape it. And we see that happens every day, like in stock market, for example. So researchers like Juan C. Perdomo have formalized how this dynamic can make static models increasingly misaligned with reality. So in this context, legacy isn't about how old the model is, it's about how deeply it's entangled with the system it influences. A model can be technically modern and still be operationally legacy in that respect. So I just want to end this video with this. All these points about legacy system, I will say across software infrastructure and modern learning and machine learning, the pattern is really the same or very similar. So legacy systems persist not because they're better, but because they're embedded in people, processes, and risk structures that can't be replaced independently. Once software becomes infrastructure, replacement stops being a technical problem and becomes a systems problem. So that's it for my video. I hope I gave something to think about. I really thought about this for a long time and wanted to see how I can formalize the idea in my head as well as writing it down. It really helped me to look at the systems differently and just really fulfill my curiosity when it comes to legacy systems.